Hello everyone, am I audible?
Yes, ma'am.
Okay, by the way, I think you know that there is this GATE test, mock test series that is started from 2 to 5 on every Sunday. So you may attend this series. I haven't gone through the test series yet by myself, but one way you can prepare for January is like for 1 week, you just revise all your syllabus and give your test series and then analyze where you have done mistake in your exam and then revise again and give your test series. So before a main gate exam, you may be able to give 4 to 5, I guess, and you will be able to practice it very clearly.
Happy New Year, ma'am.
So happy new year, all of you.
Happy New Year, ma'am.
See-
Happy New Year, ma'am.
Happy new year. We will start with this topic of phase space is a continuous of this stability and instability analysis of previous class. So I just thought it will be good if we finish this topic as well. So you may also have the same time, your mock test series as well, 2 to 5, and your classes between 3 to 4. So if you want to skip the classes to attend the mock test, you can do that. All the lectures will be available on YouTube lectures. So I will record it and then post it on YouTube. You can watch it later. So if you wanted to join test series,
Ma'am, mock test is not opening.
it's not opening.
Yeah, ma'am.
So I will ask the coordinator when it will start it functionally. So okay, we will start today's class then. So this is the concept of phase space, and it is kind of more of semi-classical in the sense we are learning more of a classical theory, classical mechanics part, but there is this quantization part which will make it to semi-classical. And it's mainly we have to learn how to draw the phase space trajectory. Last time we have shown that if we know how our potential is behaving as a function of r, then we can say about the trajectory of particle just by analyzing the plot of this v versus x graph. But here we are what we are saying is if we know the momentum versus x, the phase space here is momentum versus x plot, then we can say a lot of things about the trajectory of the particle. In Newton mechanics, you have known that if you know the position of the particle and the velocity of its particle, then you can say how your system is going to behave at any time later. And you can say it with very high accuracy. But in case of microscopic particles, they generally don't use Newton's mechanics. We are using quantum mechanics, and particle is not represented by their position and velocity. They are represented by wave functions. And since we cannot localize wave functions, so their position are kind of spread locally. And this is from this Heisenberg uncertainty principle. This says that if we can measure the x component of momentum with some accuracy delta px, and then we cannot measure its positions at the same time with an accuracy which is greater than delta x. And Heisenberg uncertainty principle give a relation between delta x and delta px, that much is the accuracy by which we can measure its position and momentum directly simultaneously. So it says that if we measure the positions of the particle accurately, then its momentum we cannot measure simultaneously. Similarly, if we measure the momentum very high accuracy, then position always going to be uncertain. So we have to kind of compromise between these two. We have to measure the momentum to some accuracy and its position to some accuracy. And this relation P between P and X, this is also used in the same phase space. In phase space, we plot between P and X to see how the particle is going to behave under different potentials. For example, you are familiar with this potential Vx of 1 by kx square from the spring potential. So in which potential have parabola form. I think you know that if you have the form of y alpha x square, it's a parabola. So same thing is here. So if you plot Vx versus x, the parabola. So if you write total energy of the particle and it is conserved for conservative systems, so the relation between P and E is turns out to be elliptical. So I just rearrange these terms. I take E as a constant and like find the relation between P and X. So just rearranging this term, if you look at this will become equation of ellipse, which is x square by a square plus y square by b square equals to 1, with a and b as major and minor axis. So with this potential, the equation is kind of ellipse. So your this will become a phase space trajectory for your potential b x equals to 1 by kx square. So we have to in exam you just ask for different kind of potential. What will be the phase space trajectory? And we will just have to draw by writing this total energy and finding the relation between P and E. So there is one more thing in this concept is classically we think that the energy could be in 0 to infinity. Like I can give any values between 0, 0.1 to 0.3 something, any continuous value between E 0 to E. But in quantum mechanics, the energy level are quantized. And you know that the energy level can take only discrete value for n equals to 1, n equals like that. So here what it says for Sommerfeld quantization rule, it says that if we plot between P and X, if we plot phase axis space diagram, then the area under the curve for this diagram is always going to be quantized. And this relation says that the area under the phase space diagram is going to be quantized. And this is related to the quantized level of energy, and we can even prove this thing for a very simple case of harmonic oscillator. For example, if you have a simple pendulum which can move between an amplitude of plus A to minus A, so basically an amplitude of total movement of 2A in x direction, then its energy can be written as kinetic energy plus potential energy. And I just write the potential energy as 1 by 2 m omega square x square. So it's just the kx k term. Previously k term is just 1 omega square here. And you just write p by just taking this term on this side and just taking square root of this. So if you plot p versus x, it will become an ellipse that we have shown here, and it is moving between plus a to minus a. So we have to calculate the area under this curve phase space diagram. So p value is replaced by this, and your dx can take value from minus a to plus a, and we just integrate it. And since we have a variable e here, so we find the relation between this variable E and A. I think you have known that if your pendulum is reached to this maximum height at this position, its total kinetic energy will become zero. So your potential energy will become m omega square A square. And once its kinetic energy will become zero, it just turn back towards this side. So at this position, at x equals to A, your total energy will become this your potential energy. So I just replace E with this relation here, And just to integrate it, I just put x is equals to a sine theta as a simple variable, the way simple we do integration. And once we do that, this is a this is the term that is turned out after integration. And then I just put a square back with this relation e. So you know that the angular frequency omega is given by 2 pi nu, where nu is the simple frequency 1 by t. So if you look at close p dot ds, this is the term. I just take it and put it here. So this will become ey nu. It is simple algebraic manipulation. You can do it yourself. And Bohr-Sommerfeld theory says that if you take closed integral of p dot dx, that is the area under the curve of t versus x diagram, it always going to be quantized. So I just put e nu by nu as nh. So this will become your Planck's quantization rule, which says that every energy level is kind of quantized when you are talking about microscopic particles. So we started with phase space diagram, and we shows that if you take the area under the curve of this diagram, it is always going to be quantized. So our main focus throughout this kind of question is just to draw the phase space diagram and show simple integrations and put it equals to quantized levels if this is asked in the question. So one of the simple, there are certain properties of this phase space curve. This says like these two lines in phase space. For example, if I have this energy level E1 and I have another energy level E2. So for E1, I have a bigger ellipse here, and for E2, I have a smaller ellipse. It depends on where I think I haven't specified you. Just if you have your potential like this and your energy is E1, then your major and minor axis, as we have known in this plot, your major and minor axis will depend on your energy E. So your energy E is given by this. So your ellipse axis depend on how much energy is your total energy. If you have larger energy, then you have bigger ellipse, and if you have smaller energy, then you have small ellipse. And these lines of different phase space curve, they do not intersect in any phase space. But if you have a non-conservative system, like if you have a friction in your system, then what friction does is your particle kind of slow down with time and eventually it just stop and your energy dissipated more in compensating friction forces. So in that case, your momentum is kind of kept on decreasing and eventually it becomes zero. So in case of non-conservative, it will be more of a spiral phase space diagram. And if it is a conservative, they will be like flat lines as it shown here. And there is another thing that we have talked in last class. It's about the stable equilibrium point and unstable equilibrium point. So if you have a stable equilibrium point, that means if you have a potential and mm, it has more of a minima here, then if you displace your particle slightly, it will come back to its original position. That means your particle is kind of bounded between these two walls of your potential. So if you have a stable equilibrium point, your motion is kind of bounded, and bounded motion is generally represented by these ellipses. But if you have an unstable equilibrium point, then your motion is like your particle displaces slightly and it just move away forever. So you can just show this by a simple diagram in phase space that we will see how to draw about unstable equilibrium point. Otherwise, it will be very much like these hyperbolas. We will see some question about unstable equilibrium point as well. So the step for drawing the phase space diagram is we just plot Vx versus x and find stable and unstable equilibrium point and draw the closed loops like ellipses around bounded point. And for the unstable points, we just draw hyperbolas. It just move away forever. if you just displace the particle. So these are the some questions in GATE exam. So this one question is about unstable equilibrium point. So you have given in this question that the Hamiltonian of a particle of mass m is given by this relation. Which one of the following figure describes the motion of particle in phase space? So you have to create phase space trajectory. And if you think, look at this, you are given a generalized coordinate system. So instead of giving x and y, you are giving q as coordinates. So I just replace it with x for simplification. Your momentum is v. Hamiltonian is your total energy of the system. And if you look at your Vx versus x graph, it's just like y equals to minus x squared kind of graph. It's like inverted parabola. So this is kind of more, if you remember your last class, in that class we have shown that whenever you have this kind of potential Vx, this will lead to unstable equilibrium point. So this is the unstable equilibrium point, and we have to find the phase space trajectory. So if one way to do there are certain rules that you follow when you are trying to draw this phase space trajectory, and one is that as your phase V is increasing, your P is decreasing. See, your total energy is given by kinetic energy plus potential energy. So if your potential energy is increases, your kinetic energy is decreases, that means if you have Vx term which is increases, then your P square by 2m terms, this is going to be decreased. So if you draw your P for this case, here your V is potential Vx is some constant value. Okay, I will show you for the bounded case, then we will plot the unbounded one. So this is the bounded case. I hope you understand what my means by bounded. It's a stable equilibrium point. In that case, if you calculate your P, it will become 2m E minus V. And I just take V as like 1 by kx square. So your P square will become 1 by kx square. And at x equals to 0, your P can take two values plus minus square root of 2me. So your x is 0. So at this axis, if you take P versus x, you can have two value 2me and minus 2me. And around stable and equilibrium point, you are kind of have more of an ellipse that we have seen earlier for this case already. And when we put for this axis, we have to put P equals to 0. And in that case, it will become n is equals to 1 by kx squared. And x will become plus minus 2e by k square root. So these are two values, square root of 2e by k and minus 2e by k. And through these 4 points, we form an ellipse. And this is for the case when your system is kind of around bounded. And when your system is unbounded, px versus x is like this, then it will become an unstable equilibrium point. So your system and p versus x flows will be opposite. You just flip in opposite side or like this. Or if you try to write it more by yourself, you can write it in this form. I will do it. So your kinetic energy here for the unbounded case is p square by 2m, but your potential energy is minus of alpha x square by 2. So you can write p square as 2m e plus alpha x square by 2. So again, you have for x equals to 0, p can take 2 value plus minus x equals to 0, p can take value plus minus square root of 2me. So these are two values on p versus x. But as I have shown you that if your potential energy is increases, your kinetic energy is decreases. And since your potential energy is kind of decreases, it is in negative x, negative direction. So your potential energy is kind of increasing. You get my point? Your V is decreasing here. So your potential energy is kind of increasing here. And this is true for positive value of x as well as negative value of x since x is in the form of a square in this expression. And the same is true for negative value of p as well. So you have two plots here. And you can also exchange the role of p and s to see how the plot is going to behave around x-axis. And if you exchange this role, then it will become alpha x square by 2 equals to p square by 2m minus e. So it's become more of an, if you put p equals to 0, so your, isn't there something wrong here? Negative e inside a square bracket. Is it given alpha is positive? No. So alpha can take positive and negative values. So if I put p equals to 0, so x can take any values, become 2e by alpha. Although there is a negative sign, but alpha can be negative, so it will compensate. So it can take two values. So we have two values here for 2e by alpha. I just did positive by taking mod of this. And we have to see that for the x, it is again like parabola in P. So we have two parabolas here. So this is the kind of plot just exactly opposite to, yes,
हाँ मैम, से आपने पी की दो वैल्यू निकाली, पी इक्वल टू प्लस माइनस रूट टू एम ए,
हाँ,
ठीक है।
yes,
पी को हमने वाई एक्सिस पे रखा है, ठीक है। आप बोल रहे हो कि
yes.
अगर पी पॉजिटिव है तो उसके कोरस्पॉन्ड जो पोटेंशियल होगा वो नेगेटिव होगा।
This is given
यस
in the question that potential have a negative form.
यस यस, अगर
I
पी
just
पॉजिटिव है तो
said
इसका पोटेंशियल मतलब नेगेटिव है,
yes.
एक्स एक्सिस के नीचे की तरफ आएगा, है ना।
Yes, the main thing that you have to remember is if your P is increasing, then V is decreasing. And here V is already decreasing, so your P has to increase. That's why the plot is towards upside. And the opposite is the true for the case when you have just plus sign here. So in that case, your potential is increases. So in that case, your P has this kind of form. It is decreasing.
यस मैम, एक बार ये प्लॉटिंग दोबारा बता दो आप,
For
जो अभी आपने की।
this one case,
सो पी इक्वल टू प्लस माइनस रूट टू एम ई।
okay, yeah, this one.
Yes, ma'am.
I will tell you again then. It's a simple thing that it, I think you are familiar with how you do plotting in x and y axis.
Yes, ma'am.
For example, if you are given this kind of simple equation y is equals to mx
Yes,
plus
yes,
c,
yes, yes.
just put x equals to 0 and you find y is equals to c, and this is your y-axis, this is your x-axis. You put x equals to 0 and you find y equals to c. So this is your 1 point, and then you put y is equals to 0 and you find x is equals to minus m by c. So you find another point which is m minus m by c, or y equals to 0, and you just plot it. So the same
Yes,
kind of
yes,
thing
ma'am.
we use here, just to find out where these things are cutting on x and y axis. So one thing that you have to remember is, if you have a stable equilibrium point, you are kind of have bound motion like this. And if you have unstable point, then your motion will be unbounded. It may be generally represented by hyperbolas, yep, or parabolas. So in that case, here your motion is about unstable equilibrium point, so it's an unbounded motion, and you have negative sign here. So energy is given by P square by 2m minus alpha square by 2. So I just put x equals to 0. Oh, sorry. First, I just simplify this equation. P square will become 2m e plus alpha x square by 2. So P will become plus minus square root of this term. And I just put x equals to 0. So your P will become plus minus square root to me. So if you take your P versus x, for x equals to 0, you have 2 points on P axis. One at square root of 2me, another one at square root minus 2me. Now you remember, if your potential is increasing, your kinetic energy is decreasing. Here it is represented by momentum. If your potential is decreasing, the kinetic energy is increasing, so that your total energy will remain constant. So here in the question it is given that your potential is decreasing like this, parabola type. So as your potential is decreasing like this, your momentum is increasing exactly same like this form. And it is true for x positive value and negative value, since x is in the form of square inside this p expression. So you just take the same form for positive value of x and negative value of x. And you have two values of p plus and minus. So you have just again the same form for the negative. It's kind of symmetry.
मैम
And
मैम
the same thing.
जो
Yes.
मैम एक मिनट, P इक्वल टू प्लस रूट टू एम ई के लिए जो आपने ये परवलय खींचा है, ये एक्स एक्सिस से ऊपर की तरफ खींचा है ना,
Yes.
इसके कॉरस्पॉन्ड है ना, प्लस टू प्लस रूट टू एम ई के कॉरस्पॉन्ड।
ये प्लस के लिए।
ऊपर वाला प्लस के लिए और नीचे वाला माइनस के लिए।
हाँ.
यस यस।
Okay. And the same thing is true for the x plots also. So your plot will
या
become kind of symmetric since it is symmetric in t and
यस
x.
यस यस मैम।
So you're symmetric in x. The main point here in this question is the direction. If you look at the all plots are same, but the direction is different. So there is this thumb rule you always remember whenever you see this direction. If your p is positive, then direction will be toward positive x-axis. And if your p is negative, then direction will be negative x-axis. And this rule is coming from this Heisenberg uncertainty principle. Delta x, delta px should be greater than h cross 2. So your this term is positive. So to make this term positive, if your delta p is increasing toward positive value, so your x2 has to increase in positive value so that total multiplication will remain positive. So in this question, if you look at this quadrant, your x is positive, your p is positive. So your direction will be for this plot around toward the positive x-axis direction. So this is the direction for these plots. Here your p is positive, but your x is negative. So your positive direction is this direction. So in this quadrant, your direction will be given by this. And in this quadrant, your p is negative. So and negative x direction is given by this. So this is how your direction will be. And in this case, p is negative, so negative direction is this. So this is how you define your direction. So you just look at the plot. In this plot, your p is negative, but direction is in positive x-axis. So this one is wrong. Your p is negative and direction is around positive x-axis. So this one is also wrong. And p is negative and direction is positive x-axis. This one is wrong. So this one is the correct answer. This is how you see these plots. Okay. I hope you
मैम,
understand this point.
यस
Yes.
मैम दैट इज क्लियर। मैम हार्मोनिक ऑक्सीलेटर की जो मोशन होती है वो बाउंडेड होती है अनबाउंडेड?
हार्मोनिक ऑक्सीलेटर की बाउंडेड होती है डिपेंडिंग ऑन द साइन ऑफ योर कांस्टेंट के हियर द दिस कांस्टेंट के become negative ना it become minus alpha that's why it become unbounded. You can plot your potential. I think you know how to plot y is equals to x square, so its potential is have a minima, and whenever you have minima that means your motion is bounded. If you do not have any minima then your motion is unbounded.
मैम ये पोटेंशियल एक्स इज इक्वल टू जीरो पे इसको एक्स एक्सिस को टच करना चाहिए ना?
That one is right. I just draw pictorially. This one is the correct plot.
यस
I'm just telling you if your sign gets flipped, then your potential gets flipped, and that make your motion unbounded.
मैम
तो
ये
आप
जो
बोल रहे
स्टेट
हो मैम, एक मिनट मैम, हार्मोनिक ऑक्सीलेटर की जो मोशन होती है वो अनबाउंडेड होती है, राइट?
It's depend on your size, sign of this factor.
मैम ये तो प्लस का आएगा ना, प्लस के एक्स स्क्वायर बाई टू।
Yes, if you have plus kx square by 2, then you have bounded motion. If you have minus kx square by 2, then it is unbounded.
यस मैम, थैंक यू, क्लियर।
Okay. Yeah, Kaushik, you were asking something.
मैडम ये जो स्ट्रेट लाइन बीच में दे रखी है ये कौन सी ट्रेजेक्टरी को सिग्निफाई कर रहा है?
This one, this
हाँ
one
यस।
is known as separatrix. There is this term separatrix. Just it to separate different type of motion, unbounded to bounded motion. This kind of motion, if you wanted to separate in phase space, then you just use this separatrix. Sometimes you might have this kind of motion as well, like you have bounded and then you have unbounded. So in that case, your separatrix will become like this kind. So it's just to separate two kind of motions.
ओके मैम, थैंक यू।
Okay. So this was question from GATE 2017. The phase space trajectory of an otherwise free particle bouncing between two hard walls elastically in one dimension is. So we have to find the phase space trajectory. You have to remember you are given free particle. It is bouncing between two hard walls. And I think, and these are elastically bouncing between these two. So this kind of example you have seen in your quantum mechanics. If you have a particle in an infinite potential well, in that case, particle motion is kind of elastic and it is kind of bouncing between these two hard balls. So from that analogy, we can say that our potential has this kind of form. It has infinity walls, very hard walls, that is mean by here, and it can elastically move between these two walls. And what is the phase space trajectory? So I can represent my potential as v equals to 0 between these two walls. and it infinity when x become greater than the wall distances. And your energy will be p square by 2m plus p. Our p is 0 inside the wall. So I just keep it 0. So your p can take value plus minus square root of 2mv. So it has two value, square root of 2mv and minus square root of 2mv. And at x equals to L and y is equals to L, your potential is 0. So this is your phase space trajectory. It's kind of constant. It is not changing with your potential. So your potential is 0 here. So P is kind of constant. And at this position, it will become infinity. So your P will become kind of 0 at this position. So it become rectangle in phase space.
मैम
Yes.
इसमें डायरेक्शन
Okay. So direction is always going to be same. The phenomena. For positive value of P, direction will be around positive x-axis. So this is how your positive x-axis direction is. Here your P is negative, so your direction will be around twice negative. And here your P is also negative, so your direction is like this. And here your P is positive, so your direction is around positive. So this is how your direction is. हाँ.
मैम इसका अगर मतलब ऑप्शन में अगर स्क्वायर और दे देता ई ऑप्शन में तब स्क्वायर सही होता है या रेक्टेंगल
Oh, that depends on in. Then in that case, they also give length because this position which is cutting here is depend on
मैम
your length.
मैम
L
इसमें तो
minus
हम
L.
सिमेट्रिक पोटेंशियल वेल ले रहे हैं
They are taking here symmetric potential well, but they are giving some relation between L and your energy E, or maybe L and your potential P, or momentum P. Only then you can say what is the relation between these two terms and can decide whether the lengths are same or they are different. If you are not specified something, then you always take it as rectangle.
मैम इसको सॉल्व करेंगे तब ये कैसे पता चलेगा कि हमें सिमेट्रिक पोटेंशियल वैल्यू लेना है एसिमेट्रिक नहीं लेना
Even if you can take asymmetric, then you just shifted your parabol rectangle around this axis. I just take it symmetric around x equals to 0. So my rectangle is symmetric around x equals to 0. So you can take it here also. If you take around x equals to a, then your whole rectangle will shift it around x equals to a. But it will remain rectangle.
या क्लियर मैम
Okay. Yes. So this is the next question from GATE 2018 exam. A particle move in one dimension under a potential Px equals to A mod S with some non-zero total energy. Which one of the following best describe the particle trajectory in phase space? So we are given a potential which have the form alpha mod x. So if you plot potential Px versus x, it will be like this. For x less than 0, it is minus x, and y equals to minus x. The graph is like this. And for x greater than 0, it is positive x. And this is y equals to plus x. So combined will form this kind of Vx plot. And you can see it have a minima. That means there is a stable point. So we are kind of have bounded motion in this case. And you can find that bounded motion by the same. You calculate the total energy, which is p square by 2m plus Vx. And for x greater than 0, this is your energy. Then you find P again. So if you look at this relation, P square equals to 2me minus alpha. So I think you are familiar that y square minus some constant a minus x. So this kind of plot is this. So it is a parabola, and a parabola is in with an opening in negative x direction. So this is the parabola like this. And it is going to cut your x-axis where your p is 0. So if you put your p is equals to 0, then you can find it is cutting x-axis at e by alpha. So this is your, this plot is cutting. And for x less than 0 case, this is your total energy and sign will become negative here. I think you know that how to open mod x equals to x for x greater than 0 and minus x for x less than 0. I just use that. So your p square will become 2me plus alpha x. So it is again parabola. And this have the form like y square equals to a plus x. So in that case, your axis is cut at a position where your p is 0. So it will be minus e by alpha. So this is your second parabola. So these two are cut. And when you put x equals to 0, then again you get plus minus square root 2me. So this is how your phase space trajectories look like. So option is correct here.
मैम इसमें मतलब ये देखेंगे कि ये पैराबोला कहाँ कट कर रहा है उसके हिसाब से पैराबोला खींचेंगे राइट
हाँ हाँ. Generally, if you write this equation, na, kinetic energy plus potential energy, you get some experience how your phase space trajectory will be. And most of the time, it is either hyperbola or ellipse or parabola. Only three kind of things that I have seen in my questions.
ओके
For example, this was a question from GATE 2019. A ball bouncing off a rigid floor is described by potential energy function Px equals to mgx for x greater than 0, infinity for x less than 0. So if you look at this potential and if you look at the this potential Vx equals to a alpha mod x. So if you put x equals to if this potential is kind of same, alpha x for x greater than 0 minus alpha x for x less than 0. So I just put this term as 0 in equals to infinity in this question.
ए इज करेक्ट
Kind
ऑप्शन
of, yes. So there is
यस
a
मैम
step
ए
here
हो जाएगा
at, yes. So at this position, your phase space kind of 0 in this case, where your potential Vx will become infinity, your P will become 0. And then you have to find which phase space represent the correct one. So again, for x greater than 0, you just write your total energy expression, find the P square and x relation, how they are going to behave. And you can see p square and x, it kind of become parabola. And it cut the x-axis where your p is 0. So you just put p equals to 0 in this expression and your x will become e by mg. And when you put x equals to 0, you can find where your y-axis is cut. So it's kind of parabola. And to determine the direction for positive xp, direction is this one. So this is the direction of your phase space. So this is kind of phase space trajectory. So this is the correct option here. And the same question was from GATE 2019 and the question number 13. In this question, you do not have to plot the phase space trajectory, but you have to find how your energy is dependent on your F. Here the potential is given of the form F mod X, the same form, and its ground state energy is estimated using uncertainty principle, then how your energy is 0 proportional to your function f. So you just write, we just go back to our discussion in which we says that the cross integral of p versus dx is equals to nh. That is the phase space curve, the area between phase space is kind of quantized. So we are going to use this relation here. So we plot our phase space diagram as we have plotted earlier, and then we have to just E by instead of E by mg or E by alpha, I have just E by f here. So one way to do calculate this area under the curve that you have learned in your 12th class. Uh, You just take it for one quadrant and just integrate for all the four quadrants. So I just take it for negative value of x since it will give you positive inside. So we just write it here, we calculate p square, and if I take it for negative value of x, then it can become positive. And put the value of p inside this integral and integrate for negative value of x is vary from minus e by f to
मैम
0. Yes.
मैम इसमें जो हम पहले वाला एरिया निकाल रहे हैं तो इसमें इंटीग्रेशन की लिमिट माइनस ई अपॉन एफ से जीरो
So how I
क्यों
take
नहीं
this
है
limit? I am in this question we are calculating for this quadrant. So I take the negative value of x in the question x less than 0. So x less than 0 we have two quadrants. So for positive value of p we have this and for negative value of p we have negative quadrant. So we have take the positive value of p so we just integrate for minus e by f to 0. This is the area under the curve. You just integrate this curve and you will get the area. I think this is how we do in 12th class also. If you want to, if you have a square or circle and you are given a radius minus 8 to 0 and you wanted to integrate this area, then you just minus 8 to 0, you integrate this surface. This is how we do area under the curve. I hope you are able to get how I'm taking the negative limit.
या मैम
Okay. So just to take the integration simplify, I just take this variable as t and differentiate it and replace x by t, and this will also change my limit. So I just put minus e by f in this expression, so it will become 1, and if I put 0, then it will become 2. So I just change my limit accordingly and integrate this expression whole. And in this expression, I just put it equals to nh from Bohr quantization rule, and we get the relation between E and F with simple algebraic manipulation, and E is proportional to F to the power 2 by 3. So in this question, it is given that how E is depend on F, but most of the time they will also ask, for example, if they are not asking for the ground state energy, they may be asked for, first excited state. So if your ground state is n equals to 1, then your first state n will be 2, then your energy will be proportional to 2 to the power 2 by 3. So sometimes they may also ask how your energy dependent on your quantization factor. So that you will find it from this relation directly. So whenever either they ask this thing or the quantization, create your phase space and put your phase space E dot dx equals to ns. And when you do that, you can get the right answer. And in today's class, we have learned how to draw phase space trajectory and solve the question from previous year. So if you have any doubt, you can ask. In the next class, we will solve the oscillation that I have promised in last class. I just thought it is related to stability and instability, so I just cover it here. You people can ask your doubt.
मैम नेक्स्ट क्लास में इनर्शिया टेंसर कराओगे हेलो आवाज
No,
नहीं आ रही
oscillation part is still left now. You people have asked to me to cover this oscillations in a spring case when you have two or more spring connected to a body and how their problems are solved. I have seen some question was asking get exam based on this simple calculation. So it will be good if we cover that. Okay. So you have any doubt?
मैम
Yes.
मैम नेक्स्ट क्लास में क्या कराओगे आप?
Oscillation करा दूं?
हाँ चलेगा मैम.
Or is there any specific topic you want?
मैम एक चीज़ और बताना नेक्स्ट क्लास में
हाँ.
ये ऑक्यूलेशन करवा दो मैम. मैम
Yes.
हेलो.
Hello.
नेक्स्ट क्लास में आप डिग्री ऑफ फ्रीडम भी समझाना मैम कि डिग्री ऑफ फ्रीडम कैसे
Okay.
निकालते हैं.
Okay.
या
I think that is part of this oscillation also.
ओके मैम. इसमें पूछते हैं मैम इसमें लैग्रेंजियन और हैमिल्टोनियन से पहले छोटा सा टॉपिक आता है उसमें डिग्री ऑफ फ्रीडम निकालना है.
अच्छा.
हाँ आप गेट 2020 का क्वेश्चन पेपर देखोगे ना उसमें डिग्री ऑफ फ्रीडम का एक क्वेश्चन पूछा हुआ है.
Okay.
Yes.
I will cover that in next class. Okay
मैम ये
then.
फेस टेस्ट ट्रेजेक्टरीज में भी है थर्मोडायनेमिक्स में है ना.
हाँ थर्मोडायनामिक्स में भी है. तो
इसको मैंने कई बार
इसका भी
ट्राई
पार्ट
किया था समझने के लिए. कई बार ट्राई किया था बट आज सही से समझ में आया ना.
ओके. इसको पार्ट ले
थैंक यू
सकते
मैम.
हैं थर्मोडायनामिक्स का मे बी क्लासिकल का भी और क्वांटम का भी. ये बीच में आता है ना.
यस यस.
ओके.
थैंक यू सो
Then we
मच
will
मैम.
meet next class. Okay, bye bye.